welcome. I'm Ron Miller with FPrin LLC. Today we have one of our engineers at FPrin, Liam Parrish, who is with us today to describe a unique, simple to use visual measurement system that he's developed for the company. This visual measurement system allows an engineer, when they're developing a particular design, to gain and understand the position, velocity, and acceleration of a particular part of that design rather quickly and rather efficiently, and allows for a speeding up of the evaluation designs, and is an advantage that we have here at FPrin LLC. Hi, Liam. Thanks for joining us. Can you give us a little information about yourself and about the visual measurement system, or as we'll call it from here, VMS?
Hey, Ron. Thanks for having me. My name's Liam, as you mentioned, and I'm a mechanical engineer here at FPrin. I've been here for about 9 months, and I've been working a little bit developing this visual measurement system for FPrin, and the sort of inspiration for this system came from when we were working on a particularly small device and wanted to know how some of the internal components of this device moved. So the outer shell of this device was clear and see-through, but we had no way of measuring the position or velocity of these internal moving components. So I thought a visual measurement system would be a really nice and simple way to accomplish that.
Fantastic. Can you describe the system itself and how it works? And I think you have a graphic that you can show everyone as a flow chart to describe exactly what's going on while the VMS is working.
Sure, Ron. Yeah, I can go over how the visual measurement system works. So first of all, the visual measurement system is a MATLAB application. So it's based in MATLAB with no toolboxes. And so the first thing that MATLAB will do is it'll import the video file. So what this does is it uses built-in MATLAB commands to take a video file that you've recorded, like on your phone or some other camera, and it'll take it and convert it into a file essentially that MATLAB can read. And then the next thing it'll do is it'll deconstruct the video file into discrete frames. And then once we're in our sort of discrete frames, the algorithm will go through and segment images using a specific method called k-means clustering, which we'll talk about a little bit later. And then after we cluster this image into discrete objects, we calculate the centroid position of each cluster. And then once we have those centroid positions, we can use numeric derivatives to evaluate the velocities and accelerations of the centroid of each cluster over time. And that gives us our object motion data. And then something that the visual measurement system can do to help speed up analysis is we can actually export a video file with those velocity vectors overlaid and the location of each centroid. So that makes it really easy to identify what's going on in our assembly.
Thanks for that, Liam. The k-means clustering, I'm unfamiliar with it, and I'm sure some of the folks that are watching this will be as well. Can you go over that a little bit more in depth?
Sure, Ron. Yeah, let's talk a little bit more about what exactly k-means clustering is and how we can use it in image processing. So on the left here, I have a sort of sample image of a bunch of balloons. And what k-means clustering does, in the way I've implemented it, is it segments each image based on clusters of color. So the first thing we do is we take this image and we plot every pixel as its red, blue, and green components. So what I'm doing here over in this plot on the right is I'm plotting each pixel in this image as its RGB components. So that's what gives these different points its sort of coordinate in this three-dimensional color space. And then what we're doing is we're using k-means clustering, which is an iterative algorithm that moves these black X's close to these centers of color. So you'll see as the iteration number increases, these centroids move towards these centers of color. And sometimes it works really well and it identifies the center of color really precisely. So a good example of that in this image is the blue X, and moves as the iteration number increases towards the center of this blue cluster. And then once it finds the center, it just kind of sits there. But another example is sometimes when objects have similar colors, the k-means clustering algorithm can get a little bit confused. So an example of this is this centroid right here, where you notice it's kind of stuck in between the gray, purple, and pink balloons. So that would be these three balloons over on the image. And it's because those are so closely related in color. So when you're using k-means clustering, it's important to use really distinct colors to sort of efficiently segment your image.
Great, Liam. Thanks for that explanation. I think I understand k-means clustering now, which I didn't before, so that's great. I think you also built a test jig to go ahead and and make sure that it was working properly, and you compared that to some analytical data. Can you share that with us now?
Sure, Ron. Yeah, so what I wanted to do was to build a physical system and then measure it with the visual measurement system and then compare that data to a mathematical model to sort of verify that the visual measurement system was working. So the system I chose to build was a pretty simple mass spring system. And this is a physical system that I built, and there's an image of that sort of on the right. And what I did was I recorded this system oscillating given an initial displacement of 15 millimeters. And this video on the right here is actually the visual measurement system in action. And this is the output video that the visual measurement system will produce. So for reference, the green dot and green line represent the centroid and the velocity vector of the red stickers placed on the mass. And as we can see, this video looks kind of as we would expect. So the green velocity vector shows that the velocity is maximum around its equilibrium position, which is what we expect from an oscillating mass spring system. And then this plot shows the actual data output by the visual measurement system. So on the y-axis, we have the displacement of that mass from its equilibrium position. And then on the x-axis, we have time in seconds. And so as we expect, this wave looks like a sinusoid wave, which is what we expect to see from a mass spring system. And then another thing we can do is we can superimpose that simulated system data. So this is just a mathematical model of a mass spring system. And this is superimposed over the visual measurement system data on this plot. And as you can see, they show really nice agreement, which makes us believe that this system works really well.
Okay, thank you, Liam, for explaining that. Very interesting system you have there, and congratulations on the work. Can you just give us a wrap up here and give us an overview of the conclusions?
Sure, Ron. Yeah, so the visual measurement system is excellent for analyzing systems that maybe have difficult components to measure. And FPrin, it's really nice because we're able to use it to speed up our development time by quickly analyzing systems that in other ways might be difficult to measure. And so if I had to pick three main advantages for the visual measurement system are its ease of use, its non-contact measurement, and its support for multiple object tracking.
Great. Thank you, Liam. And for our audience, thank you. If you would like to learn a little bit more about this, we have a white paper that's online on our website, and you go to our resources page and you can download the free white paper there. Thanks a lot. Take care. Have a great day.